Right, so I'm Sam Stites. This is work I did with my collaborator, Austin Kong, who's over at Fidelity. And since this is NPFL, next. All right, for the overview, it's a little truncated just for time. So maybe you are in between papers of graded monads and approximation theory, and you've heard some buzzwords having to do with deep learning. And in general, and then you want to do something like make your MS Paint artwork look like something Bob Ross did, or perhaps you want to turn your horses into zebras or give yourself kick-ass dance moves. And in general, you're going to be pointed in the direction of Python, specifically TensorFlow. But I would like to kind of shine a light on sort of a new library that is currently being pushed specifically by Facebook called PyTorch. Now this is actually built on the old Torch libraries, which is I believe, one of the oldest deep learning libraries. It's about 15 years old. And it's gotten a few revamps from Facebook, Twitter, and Google DeepMind. And PyTorch is sort of the next iteration of those Lua bindings. So PyTorch is research-oriented, or the Torch libraries are research-oriented. They're not necessarily production-ready, although that's actually about to change pretty soon. And they are all sort of this deep wrapper over this very simple C abstraction of tensor operations. So what is Torch? It's actually a library called a tensor library for C++11. And it is subsuming both the Torch ecosystem as well as other libraries. You may have heard of Cafe2. That's sort of the production counterpart of the Torch suite. And it also pulls in any BLOS or LOPAC dependencies you might have, depending on what is on your system. So PyTorch professes to be Python first, but what that really means is that the C API is so simple that it needs deep, heavy integration with Python. And the underlying library is metaprogram C. It's functionally inclined, I'll say it. I'm not going to say it's infused. And this all kind of means that we lean on the host language to provide a lot of the abstractions we'd like to have. And luckily, in Haskell, we have a kick-ass host language. We have, excellent support for concurrency, for maintenance, for streaming. We have systemf, the Curry-Howard-Lambic correspondence. Yeah, it's a bunch of fun stuff. But when it comes to numerical computing, it's a little bit more lacking. Specifically, looking at the State of the Union, which is an open source document by Gabriel Gonzalez, technically bindings don't count when it comes to helping the Haskell ecosystem, or at least it doesn't for TensorFlow. But I'd like to address that kind of towards the end of the talk. Since this is more of an introduction to this tool, we're just going to talk a bit about the API, we're going to talk about internals, and then we're going to jump back into kind of an end-to-end example. There are two APIs in Hasktorch. There's a dynamic API, which is pretty much just the same as what you would expect from something like PyTorch or Lua Torch. And you can create new tensors with uninitialized memory. You can create tensors with filled values. You can create them from lists. You can create them from lists of lists. You can create them from lists of lists of lists, and more. So you might notice that in our dynamic API, everything happens at runtime. So we have to pass in our dimensionality as an argument to these functions. And of course, when we hoist that up, we can hoist that up to the type level with a static representation and with a type level list representing our dimensionality. We can also do a lot of nice things like perform any bounds checking, do any sort of squeeze-unsqueeze operations, and this is all kind of being leveraging the singletons library. In general, this is the preferred API because it allows us to take all of the error checking, hoist it to the type level, and it lets us leave the underlying code the exact same. I also want to mention that we use the dimensions library, so you're not actually looking at a NAT, you're looking at a dimensions-specific NAT, which allows you to use bounded NATs for any operations you might need. And you can also create all of these things with runtime lists using accidental quantification, and there's some helpers in that library for that as well. So Hasktorch is a bindings library. It is a bindings library with some pretty cool internals, and we've leveraged a lot of fairly new ecosystem tools, including Backpack, an automatic differentiation abstraction. We make heavy use of dependent types. We use a non-Turing language called DAL for our config files. We also have a bunch of cool stuff that we're not going to cover on the code generation to extract the bindings from metaprogram C. But I'd like to talk about Backpack first. So Backpack is sort of the origin story as well for this library. The Edward Yang, whose thesis is Backpack is the thesis work of Edward Yang. So he guest posted a blog post where someone kind of prototyped the torch bindings in Backpack. And Backpack, for those of you who are not familiar, is it's a module system. It's a mix-in library for GHC. And just to give you a little bit of an intro, in Backpack you define a signature file, which is an abstract representation of just any types or function signatures that you might have. And when you actually pull that into Haskell, you just use it as if those signatures are real. They're a real Haskell. And that piece of code would be called Indefinite in Backpack lingo, because there is no backend supporting that signature file. We would hook it up together in the Cabal file, and to make this indefinite piece of code fully arrayified, we would have to line up the backend with the signature file. And in this case, we're using byte string. We might want to use text, because all we really have to do is satisfy this signature. So we could use text, we could use byte string, you could use base, and with that you kind of get this signature where you have multiple packages with multiple package maintainers, and you can work against a unified API. And this is kind of what it looks like all hooked up. Some use cases of Backpack include primarily it can be used as an abstraction similar to type classes, except there is no type level record that you are maintaining. So it's a zero cost abstraction, and you can use it to mock and stub code for testing without the overhead. You can use it for unifying disparate packages, and we use it because we know that there are exactly 16 types in the Torch system, and for the foreseeable future, we're never going to expand beyond the scope of these 16 types. So we can eliminate that overhead. So another tool, and we'll kind of get into that a little later. So we also use Backprop. Backprop is a library from Justin Lee, and Backprop is an AD library, and that is a talk in itself, and it's in fact a talk that has happened twice already at this conference, once from Connell Elliott's simple auto differentiation, and once from the incremental lens, relational lenses by Rudy Martin. So we're just kind of gonna gloss over this, but in short, if you have a function that takes something that is an instance of num or an instance of backprop, you can wrap it in a backpropable variable. And the code, for the most part, looks the same. There's a lot of cool things going on. It's using the ST trick to make sure that it can mutate gradient. It also reifies just a simple gradient tape which is the representation of W there. And what this means is that you can evaluate the code as if it was just regular Haskell, or you can also extract the gradient, and then you have the gradient. So it's so that's pretty fun. So when creating the abstraction, when creating a library for backprop, backprop is actually it predates Connell Elliott's work, and so you basically define operations with a specific arity, and there's some work specifically kind of on my side trying to kind of re-instrument Connell Elliott's work, and we also have another Skunksworks project called Diffhask, which is an attempt from, I believe it's almost finished, from Tim Pearson to also do the same thing. So in short, this pretty much encapsulates all of the layers of this tool. We have A10, which handles any machine dependencies, unifying both the GPU and the CPU. We code gen the raw Haskell bindings, the C FFI bindings. We unify that with a backpack spec. And then the dynamic tensor functions are really just that FFI spec bundled up with where we take something like a get rank 1, get rank 2, and we unify that into like a get dims function. Static tensors have phantom types, and at that layer we can use dependent typing to ensure dimensionality checks. Differentiable operators are taking those tensors and tensor operations, bundling them into an AD abstraction. And then we have machine learning models, which are paired ADTs with their specific forward operation, which is bundled together with a backward operation. So in the end, we kind of wind up with a full end-to-end pure deep learning model. Here, this is kind of the idealized version. It's also very truncated for use of slides. So normally we would want to load data, we would want to construct our architecture, an initial architecture. In this case, that architecture is called Linnet. With that initial architecture, we pass it in through our epochs function. So we iterate over the data 3 times, 3 epochs, with a learning rate of 0.001. And then finally, we report all of our values. So this is pretty simple Haskell. Epochs is just recursion and a fold. So each fold steps through each element in the data with a learning rate.
The 32 is the number of neurons in your, is it? Or what's that telling us?
What is
the 32? Is that the number of neurons in the neural net?
Yeah, this is just an image. Yeah. It's a 32 by 32 image with 3 channels. Yeah. And of course, when we train, all we have to do is run backprop, which will give us both the forward and backward output, so we get the output and the gradient. We can also take our architecture-specific function, Linnet, and we can just tag on a loss function there. And from that, we get gradient, which we can perform gradient descent with here, doing scalar multiplication gets the learning rate, and then adding it to our network. The ADT representation is also pretty simple, and I would argue reaches a certain level of parity with the current ergonomics of PyTorch. It's a conv2D and a linear ADT. The conv2D and linear are just tuples. of a tensor of weights and a tensor of biases, and we put everything at the type level. Our forward function is comparable as well. We have this magical conv layer where we apply it twice to conv1 and conv2. We flatten, and then we apply a simple linear forward. We run through our forward, our head. And of course, linear layer is slightly less, it's slightly more verbose because we haven't quite gotten around to defining all of the defaults. But we find that it's still fairly simple, although we have to define everything up front. So some caveats to all of this is that it's not yet released, which means that it's actually just like a week or two away from being released. I found the last bug like 2 nights ago. The last bug before the release. And this is also not just for neural networks. It's important to note that these are just generic tensor operations that we're trying to expose in a clean fashion with like sort of an H matrix API with a vector style of mutation. And that's also why everything is currently in I/O, because we're trying to see how pure we can make this before, and like how to correctly represent mutation. And so yeah, this is not just for neural networks. We had a PhD student swoop in the very beginning of the project to implement like a cutting edge version of Lasso, and then he just like swooped out. There's some examples of Bayesian regression. And nobody's done variational methods. Someone might want to do that. I have a reinforcement learning library as well, which is my primary interest in this. And kind of, I think one of the coolest parts of all of this is that we are basically enabling researchers and developers to kind of come up with algebraic representations for the application side, but with Backpack, we can also kind of level up the Haskell ecosystem on the optimization side as well, because it would allow users to kind of use this unified API, and perhaps by adhering to this Backpack spec, we can start to swap out Torch with pure Haskell representations. And that's really exciting to me as well, because it's been shown before and time again, and in all of the ICFP talks, that these algebraic representations can actually have extreme speedups. Like, for instance, the one that comes to mind is Micah Zigbey's work, where he still has, I believe, the fastest k nearest neighbors implementation to date by a number of benchmarks, and he just did that by looking at monoidal abstractions. And I mean, there's a ton of work that I think can be done mixing in programming language theory with machine learning. I think it's a very exciting kind of like thing that is always hindered by the host language and implementation details, and I think it's kind of, we can finally start using them in industry too if it's all in Haskell. It's all very exciting. Kind of just looking forward to what other people will come up with. So that's pretty much the talk. I actually truncated it quite a bit, so it's actually quite short. But that's the talk. Here are the various channels you can find us at. Everything in this presentation you can find also in our GitHub repo. And thank you very much.
Got any questions for Sam?
All right.
Why don't you go first?
It seems like it's a lot of work to maintain these dimensions and types. Is there any way to, if you have an image on disk, read the dimensions of the image and then break them into the type?
Yes, we do that. Yeah. I mean, that kind of comes with just various control flow of how you handle errors in Haskell. because you can assume that there is going to be a specific type of dimensionality to your image, and you can just kind of tag that in, and we can perform just bounds checking at runtime to enforce those rules. You can also decide not to have explicit types. You can use bounded nats, but I haven't experimented with that yet. So.
But if not, you could also use template Haskell to open the compile run.
Yeah. Usually, I think people assume that they will have to adhere to a specific input size. So there is some runtime checks that have to happen.
Yeah, I'm just interested in how this project is managed. Do you have any support from commercial companies, or just kind of the big hobby project? Or
Yeah, so this is a project that I've been working on full time through Sentinel, and we're pretty much finished. It's motivated by the fact that a lot of my work is flip-flopping between Python and Haskell, and this is hopefully going to reduce a bit of that traction. It started off as a hobby project from Austin, and yeah, this is the current status.
Do you have any specific goal, or what is the main motivation of this project, or are you targeting on any specific goal?
Yeah, I would argue that a very, very heavy motivator for me is to kind of do everything in Haskell. But to kind of drive that point a little bit further, our production system is also purely in Haskell. And so anything that I put into production has to ultimately wind up in Haskell. So, but a lot of the research side has to occur in Python. So there has to be some point of translation, and this is a lot of work that I've been doing, just mostly to make that transition slightly more seamless.
So I know Edward Yang is actually working on PyTorch right now at Facebook.
Yes.
So I'm curious, is there any interaction between you and him, maybe trying to snipe him to get him to do the Haskell version? Or?
I don't think we would be able to hire him. but yeah, I mean, I bug him all the time and ask him for features, and I probably have no shit of him. But yeah.
I also want to ask, are you planning to update, I guess, the further development process of Hasktorch? Are you going to just port features from PyTorch, or you're trying to possibly add something more that's not in Python? How's that? How are you? Because you mentioned something at the end that you might want to possibly even remove the, integrate it more into Haskell, like with the backpack. Or
Yeah. So that's a thing that excites me. That's also a thing that I'm going to leave to some other soul. I would say that the current development progress is primarily trying to just hit parity with PyTorch, because a lot of the neural network operators require each neural network operator is a non-trivial amount of work to just encode the dimension checking into the type system, and that is something that we haven't done for all operators yet in the neural network library components. So once we get enough of those, then perhaps we'll be able to do more interesting things with fancier operators like diluted convolution in all three dimensions, or in spatial and temporal and etc. But in the meantime, kind of current development is just sort of taking our currently just I/O-based interface because of the FFI and starting to figure out how to make things seem more H-matrix-like, and how to encode mutation, because with tensors, you have these huge data structures, and we would like to kind of move in the direction of ST, or perhaps just kind of have this generic interface like vectors. So, yeah.
Have you thought about using like representable functors instead of tensors, instead of multidimensional arrays?
We have not. We're
Let's talk about that.
yeah.
I think you could get a lot more typed, and have fewer numbers and more composition.
Setting me up for my talk.
Exactly.
Yeah, I'm very excited
Let's
to.
stick around for dinner and stuff.
I'm very excited to that. Yes. So that is something that like mostly we've just been trying to get the FFI bindings up to speed, and since we're kind of reaching the end of that run, we're very excited to find out what we can do here in this talk to find out.
Let's look back afterward.
Yeah.
Great. Thanks very much.